Okay, so hello everyone. Today we're gonna learn something really fundamental, but almost everyone ignores it. We're gonna learn about stack. Yes, stack, your average stack, but not in the way you think. We're gonna learn stack pointers. We're gonna learn why G++ or GCC offsets the stack pointer to -4 at the start. We're going to also learn how to get the stack pointer and actually see the stack pointer and its value. So let's start right there. So first we would need a main.cpp file. We are going to do this in C++. Okay, so let me just make a function and let us return 0. That's nice. So this is a typical C++ function, global function to be exact. Now let's make a int a equals 0, but compiler is gonna optimize this thing. So we're gonna say volatile. Volatile int a equals 0 means this variable a can be changed externally, i.e. any other program could actually write on the int a's address. So we are saying the compiler, hey man, I know this int a is not contributing in the program, it's just there, it's not being used, but don't optimize it. It might change and it might be useful. Okay, so that's nice. Now let's take unsigned long a address. So it's address of a, and we're gonna unsigned long and address of a. So we got our things ready. We can start see out the a address, also null terminated, so that the terminal looks nice, and we can see the address of a. So let us see the address of a. G++ main.cpu/main. Okay, so this long integer, unsigned integer, this represents the address of a in terms of decimal number system. Obviously, if you want to know the address of a in terms of hexadecimal, you have to convert it, but this is pretty okay for us because it is easier to read and interpret. Okay, now we know well that's our a, and we are start counting a, but we want the stack pointer now. Okay, so how are we gonna get the stack pointer? First let's see what a stack pointer looks like. Okay, so we can remove all of this and make our program just like this, so that the assembly looks cleaner. Okay, so volatile int a equals 0. Let's make it some number that's easier to learn. Okay, 69. So volatile int a equals 69. Now we're gonna make it into a readable assembly. If you just pass the s tag, it's not gonna be enough readable, but if you pass this exact command, it's gonna give you a really simple to the point assembly. So we can now see we got main.s right there, and we can go and see the assembly here. Okay, So the file is main.cpp. This is the text section. Global is main. The type of main is function, and this is main. Okay, now we are saying this is the volatile int a equals 69 line. We can see here move vl. Move l means move literal, means don't change this value, change this literal 69. There is no change in this. You just have to put this literal 69 somewhere. So the instruction I'm using is at and t. This is the instruction set. This is the assembly that I'm using, because I'm using AMD CPU. If you are using Intel CPU, then you will be using Intel assembly. Okay, so in AMD we have the source first, the instruction, then the source, and then the destination. So we are saying take the 69 and move it where? In the RSP. Hey, now let's see what is this RSP. RSP is a register that stores the stack pointer. Okay, so this program has a stack dedicated to it. We want its point, the stack pointer. So the RSP stores the stack pointer. Boom, we know RSP stores the stack pointer. Well, RSP stores the stack pointer. Then what is this -4 doing in multiplication? Well, it's a way of writing. This is saying take address of RSP and go back 4. So this is what it's doing. Take the address of RSP and go back 4. Why go back 4? Is it because our int, is it because we have int a equals 69? No, we can also have float a equals 69, and let me do this, and we can again do this command and we can check. Now we got an extra step here, which is loading the float into x nm0 mm0, and this is the register that stores the floating point numbers in a 64-bit system. So this would be different in 32-bit system. So we are saying, and also RSP stores the stack pointer in 64-bit system. So if you have a 32-bit system, I think it's ESPN, something like that. I don't know exactly which register stores the stack pointer in 32-bit system. Okay, so what we are saying is move the value in x mm0 to -4 RSP. So we are saying take the value in this float point register that stores that floating point value, and then store the value in RSP at -4. Okay, so it's nice. Well, is it storing the value? No, it's storing the reference, I guess, because RSP can't store floating points. So this is storing the reference, to be really precise. But let's continue saying that it stores the value. Now we want to see where exactly is the RSP. What's the address of RSP? I can't just type unsigned long address of RSP is an RSP, because I don't have the access to RSP in C++. I only have the access to RSP in assembly. So but we are still gonna write C++. We are not gonna write assembly in a different file. What we are gonna do, first let us get the address of A and assign it to this, but let's also long. Okay, that's good. We can also start cout just for our reference. Start cout a address with a null terminator. Now what we can do actually is we want address of RSP. Well, let's first make a variable where we can store address of RSP, and don't assign it yet. Now we're going to do some magic. We're going to type assembly volatile, and I'm gonna explain just in a moment what I'm doing right now. It looks like magic. I'm saying and RSP address. So what did I type here? Well, ASM volatile is actually a way of embedding assembly in your C++. So you could embed your assembly in the C++ file without leaving the C++, and you could write assembly here. So what I have done, I have tell, well, this block is assembly, so ASM, and the next things are gonna be volatile. Volatile means it can change without the compiler knowing it is changed. So volatile just says, well man, don't optimize this line. So because this line is just a non-performant, which means that this line is just there and not providing any real meaning to the whole main function. And why it is that? Because ASM will be compiled, then it would provide the RSP address. Without compiling, it's just a line. So what I said is volatile. Now let's move on to the real thing. I have written assembly over here. This is assembly, AT&T assembly. What I have said, move the value stored in RSP. So RSP stores the stack pointer. So I'm saying move the stack pointer to RAX. What is RAX? RAX is another register. That's a general purpose register. So we can use it to store values. Okay. So I said, well, take the value in RSP, that's the stack pointer, store it in RAX, and this whole method, this whole operation is just in read mode from the C++ side. So I said, execute this assembly, this instruction of assembly, and read. The operation that is executed is only a read operation. So I'm saying read from what? From RAX. What? RSP address. So whatever data is being transferred from RSP to RAX is read into RSP address. That's a way you can understand it. Okay, it's not accurate, but it's close enough. I can actually see out my RSP address, and I'm gonna tell you I'm gonna just tell you a magic that happens here. So we are start outing the RSP address, and now let's run the program. Boom, what did you notice? Well, this is the first cout and this is the second cout. Did you notice something? The first cout holds the address of float a equals 69, and it's this long number. The last you could see it's 16, and the address of stack pointer is almost the same until the last. The stack pointer, okay, so this is the variable a and this is the stack. Well, the stack pointer is 4 behind my a variable, and we actually noticed that in assembly, right? But in assembly we said, hey, move 4 back from the RSP and store a. So we said, well, I'm gonna move back from RSP and store a. So the stack pointer should be 4 ahead of A, but it's 4 behind of A. Why is it that? Because the stack grows downwards. Because of the fact that the stack grows downward, this the stack pointer, though it's ahead of though it's ahead of the int A by 4, but when we look at its address, it the address is actually smaller. And what you just noticed right here, we exploited what we did, we exploited the memory. We said we are gonna, and also we can write programs that takes in the values, that takes in the addresses, not in this long format but in the hexadecimal format. And you could actually feed that into assembly and say assembly to write address at that address. So what I'm saying is, well, I got the address right here, but the program exited. So I don't want the program to exit, because if it exits, the addresses are gone. Okay, if it exits, then the addresses are just garbage. So I'm gonna say this thing, so the program won't exit until I provide some input. Okay, so program didn't exited, so these addresses are still alive. I could write another assembly or C++ program that writes in these addresses, and I could manipulate the variables inside main program from another program that's completely different from this main program. That was the best way I could explain that. So that's why we marked volatile, because we just said to compiler, hey man, some external factor could actually affect this variable, so don't actually optimize it out. It's not being used right now, but it will be used. So that's all for today's video. Today's video was a bit light, and I prefer you should go and search for assembly instructions for std in and std out, so that we don't need a C++ interface. We can directly write assembly for taking the input and outputting anything we want. We would be using that to output the address, and the std part will be to take an address and update that address. Well, we can also do that in C++, and we will of course be doing that in C++, but C++ is not really good when it comes to handling raw registers, and that's where assembly excels. So we're gonna do that next. Make sure to like and subscribe, okay? And I'm gonna come with something more knowledgeful in the next video. That's all for now. Goodbye.